Hello learners, welcome to this course on practical machine learning using Google Colab. In this tutorial, I will be discussing about on how to classify images in Fashion MNIST Dataset using Tensorflow API. So the code of this tutorial will be available in this GitHub repository. So you can find the code in this link. So now let us move on to discuss the program. So let me open the program. So first, let us connect this Google Colab into a cloud environment. So in order to do that, go to Edit, Notebook Settings. So what type of hardware you require, you select that hardware and save and connect it to the cloud environment. So it will get initialized and it will get connected. So in this tutorial, what we are going to do is we are going to take a Fashion MNIST dataset. So Fashion MNIST dataset, in the sense it contains clothing like shirt, pant, sneakers, trousers, etc. So it contains about 60,000 training images and 10,000 test images. So we have about 10 classes of clothing. And each image size will be 28 by 28 pixels and it is a grayscale image. So the labels of these images are given as 0 to 9, representing the 10 classes. So each class is given by a number from 0 to 9. And the pixel values of each image will vary from 0 to 255. So it's a grayscale image. So in order to work on this Fashion MNIST dataset, so let us install TensorFlow. So I'm going to install TensorFlow 2.2.0 in the cloud environment. So that can be done using this command !pip install TensorFlow equal to 2.2.0. So once you run this cell, the supporting packages which get installed in the cloud environment. Once the installation is done, we can import the necessary packages. So we import print functions, Unicode literals, etc. And then I also import the TensorFlow as TF, and Keras package also is being imported. Then we try to make use of a NumPy, which is a numerical Python library, which is mainly used for matrix computations. And for plotting, we try to use the matplotlib. From that, we try to take the pyplot and use that for plotting versions. So the TensorFlow is very convenient package for building and deploying the machine learning models. And advanced machine learning algorithms are available in the Keras package, which works on top of your TensorFlow. So we can also make use of the data sets available in the Keras package. So we are going to do that in this program. So once the installation is done, we can import the necessary packages and then we can check for the version of TensorFlow. So we can run this and we can see which version of TensorFlow is being installed. You can see 2.2.0 is being installed. So now let us go and take the dataset, Fashion MNIST dataset from Keras package. So in order to do that, we define this keras.datasets.fashion MNIST is assigned to a variable fashion_MNIST. From this, I try to use a function called as .load data to take the data. So when I try to take the data, I will get training images and training labels, which is going to have 60,000 images and 60,000 labels, and test images and test labels where we are going to have 10,000 images and 10,000 labels. So we try to retrieve the data from the Keras package. So let us try to retrieve the data. So once it is done, we define the class names. As I said, we have 10 classes here. So we try to define the class names. So the first class name is t-shirt or top, trousers, pullover, dress, coat, sandal, shirt, sneaker, bag, ankle boot. So these are the 10 different classes. We try to initialize the class names. Let us see how many data are available in training as well as test. So in order to do that, I am going to use a print function. I am going to use dot shape function to see how many samples are there, what is the characteristics of the image, everything we can visualize here. So we try to see the length of the training label. So how many data is available in training and how the training labels look like. Same thing we are going to do it for the test images. Let us run this. So when I run this, you can see 60,000 images are there in training data, and each image is going to be 28 by 28 pixels. So when I print the second one, length of training labels, it shows 60,000 images. And how the labels are going to be training labels, so it is defined like this. So here you can see 9. 9 represents the class called ankle boot. 0 represents the class called t-shirt or top. Right? So each class name is assigned by a numerical data. So here we can see the first image as the ankle boot, the second image as t-shirt or top, the third image is also having t-shirt or top. So like that it goes on. Same way we try to see the test data. So test data, we have 10,000 images and each of 28 by 28. So the number of test data is 10,000, and you can also see the labels associated with the test data. Then let us plot an image and see, visualize it by using the plot figure function. So I'm going to plot in train images 0th image. So we have about 60,000 images. In that I'm going to plot the 0th image. So when I try to plot this, you can visualize this is an ankle boot. Okay, ankle boot, which represents the class label 9. So then here you can see that the image sizes along rows it has 28 pixels, along columns it has 28 pixels, and the grayscale values vary between 0 to 255. So since it's a grayscale image, the pixel values vary between 0 to 255. So we try to normalize this pixel values. From 0 to 255, we try to convert it into 0 to 1. So in order to do that, I try to take the training images divided by 255. Same way, test images divided by 255, thereby the training images and test images, the pixel values will lie between 0 to 1. So we try to normalize the intensity of training and test images. So now let us plot and see the images. So I'm going to take 25 images. So for I in range 25, which means I try to take 0 to 24. 25 will be excluded. So we try to plot it and see. So we try to change the index values from 0 to 24, and we try to plot all the images and visualize. See here, you can have a visualization: ankle boot, t-shirt, t-shirt or top, dress, t-shirt or top. So like that, 25 images in the Fashion MNIST dataset are shown here. So now we have done with the data. So now we have to create a model. So what we are going to do is we are going to use a simple neural network with one hidden layer. And the number of neurons in the hidden layer, I'm going to take it as 128. So in order to define a neural network, I use a sequential function from the Keras package. First, let us make the data which is in 2 dimension to a 1 dimension, because then only we can provide the data to your neural network. So our image is a 2 dimension data which has 28 by 28 pixels. So we need to convert it into a 1 dimension data. So in order to do that, we use a flattened layer which converts your 2 dimension information to 1 dimension. So my image is 28 by 28. So 28 into 28, it becomes 784. So altogether 784 pixels are there. So it becomes 784 1 dimension data. So then after forming a 1 dimension data, we create a hidden layer which is a dense layer. So dense layer in the sense all the inputs will be connected to each neuron in the hidden layer. So I am going to use 128 such neurons in the hidden layer, And the activation function which I'm going to use is ReLU activation function. So ReLU activation function in the sense, for any positive value, the output will be a positive value. For negative value of input, it will give an output of 0. So after defining the hidden layer, I'm going to define the output layer. Again, we specify it as a dense layer. How many neurons in the output layer? We have about 10 neurons. Each neuron representing for a particular class. Since I have 10 classes, we define 10 neurons. And the activation function which I use is softmax activation function, which gives a probability score for each class. So once we have defined our model, so first we convert our 2-dimension data into 1-dimension data. Then we create a hidden layer with 128 neurons and an output layer with 10 neurons. So we try to summarize the model and visualize it. So when I summarize, you can see first initially we have about 784 inputs. So this 784 inputs goes to the 128 neurons of hidden layer. Then how many parameters we should have? We should have about 784 into 128. Since it is a dense layer, all the inputs will be connected to each and every neuron. So 784 into 128 represents the number of weights. So it comes about to be 100,352 weights are there. Plus each neuron will have a bias term. So we need to add 128 bias terms. So altogether you will get 100,480 parameters. So you can visualize here 100,480 parameters are there in the hidden layer. So then this 128 neuron output, it goes to the 10 output neurons. So in order to visualize it, 128 into 10, so it is nothing but 1280 plus 10 bias terms. So altogether you will get 1290 parameters in the output layer. So the total number of parameters is, we have to add both the things. So thereby I get 101,770 parameters needs to be trained by the model. So once our model is defined, we have to set the parameters for the model. So the parameters are set using the model.compile function. So where we have to set what is the optimizer we are going to use. So optimizer is nothing but how the weight and bias terms will get updated. So there are different schemes like ADAM, ADA Delta, ADA Max, SGD, etc. So we can define our optimizer, how the weight parameters, how the bias terms will get modified. So here I am going to use an ADAM optimizer, and we define the loss function because our model will get trained depending upon the loss function. So our ultimate aim is to reduce the loss. For reducing the loss, how the weights should get updated. Since it is a multi-class problem, we use a sparse categorical cross entropy loss function. And the metrics used for tuning will be accuracy. So let us define the parameters. Once the parameters are defined, we can train the model. So in order to train the model, we have to specify for how many epochs, for how many iterations of our data set we should work on. So that is defined. So I'm going to take it for 10 epochs. So 10 epochs in the sense, for one epoch, the complete data set will go to our model to get trained. So like that, I'm going to provide the data set for 10 times to our model. So that is what it represents, 10 epochs. So in order to do the training process, we use the function model.fit. I give training images and training labels, and how many times we are going to run this data set on the model for 10 times. And we try to see the result using verbose function. So while doing this, the updation of weights, updation of bias terms will happen with respect to batches. So here in this model.fit function, I have not defined any batch size. So by default, it will take a batch size of 32. So when I have a batch size of 32, so how many such batches will be done? In the sense, 60,000. Altogether in training images, I have 60,000 images divided by 32. So we will get about 1875 batches. So the weight updation will happen in each epoch for about 1875 times the weight updation will happen. So in a epoch, for 1875 times the weight updation will happen. So let us run this. So you can see when the first epoch runs, you can see the batches here. So 1875 batches. For each batch, the weight updation will happen. And here you can see the loss, training loss and the training accuracy. So after first epoch, you can see the losses of about 0.49, accuracy is about 0.82. So as I try to give the data set again and again for more number of epochs, you can see the training loss gets reduced, whereas the training accuracy gets improved. So after 10 epochs, you can find an accuracy, training accuracy of about 0.9095. So now let us put our test data and check how well our model has learned. So in order to do that, we use model.evaluate function. I give the test images and test labels. So then try to print the test accuracy and test loss. So when I run that, you can find that test accuracy is of about 88% and the test loss is 0.32. So now let us see how the prediction is for a particular image. So in order to do that, I'm going to take all the test images. So 10,000 test images, I'm going to do a prediction. Model.predict. So our prediction score will be available in this list. So let us print one prediction for the first test image. What is the prediction? We will try to print it and visualize it. And then I try to take the maximum value of that prediction and try to put it here. And what is the ground truth value also, we will try to visualize it. So when I run this, you can find when I print the prediction, so this prediction is for the first image in the test data. Prediction is for first image in the test data, prediction of 0. So like that, the prediction is there for 10,000 test images. So this is one such prediction. Here you can find this is one such prediction. Since we have used a softmax activation function, so here you can see it gives a probability score. So this probability score is for class 0, probability score for class 1. So like that it goes on, and this is the probability score for class 9. So from this probability score, we need to find the class with maximum probability. Which class has a maximum probability that we need to find. So that we can find here from this, everything is under 10 power minus 7, 10 power minus 10, 10 power minus 4. Whereas if you see the class 9, it has a lower, not lower, it has a maximum probability score. It is in 10 power minus 1. So since the probability score is high, what is the index for this one? This is 9. So the predicted value will be 9. What about the ground truth value? Ground truth value is also 9. So the actual ground truth value of the image is 9 and the predicted value is also 9. So like this we can visualize for each image what is the prediction array. From that prediction array we can find the class with maximum probability and that class can be assigned with that label. So in order to have a little bit more visualization, I define two functions. One is for plotting an image and another one is for plotting an array, prediction array. So for plotting an image, I take an index, prediction array, true label as well as the image. So we try to put the prediction array in a variable called prediction array, true label of a particular image to true label and image to image function. Then I try to plot it and see what is that image, and I try to take the maximum value of the prediction array. So thereby we get the predicted label. Then I check whether my predicted label is equal to true label. So true label is ground truth value. If my predicted value is equal to true label, I put it as a blue color. If the prediction and true label are different, then we use a red color. for plotting. In the array declaration, I take the prediction array and true labels. So here I define a bar plot range of 10, which means I am going to take from 0 to 9 for each classes. Then we put a prediction array with different colors. And as usual, we use two colors, red for wrong prediction and blue for right prediction. Okay, once this is done, we are going to use these functions to plot and see. So I'm going to take one test image. I'm going to take I value as 4. And I'm going to give this fourth test image, right? So 4 prediction and its test labels with the test image. So I'm going to plot it and see. Same way, I'm going to plot the prediction array also. So when I run this, you can visualize. So this is the fourth image in the test data and this is the prediction array. You can see the class 0 has some probability score. Class 1 does not have. Class 2 some value is predicted and this class is rightly, since it is represented in a blue color, meaning is the predicted value and the ground truth value are same. So here you can see in the image the predicted value is shirt and the model's confidence is about 89% and the ground truth value is also shirt. So it gives a right prediction. So let us change some other value. So I'm going to take it as 9. So let us run. So now the 10th test image will be taken. So here you can see this is the image. So the predicted value is sneaker and our algorithm says 100% it is sneaker and the ground truth value is also sneaker and the corresponding class it gives a higher value. So let us take some other value. I will take 15. So randomly I am choosing the values. So here also it shows trouser 100% prediction. So you can see, visualize that for each image there is a predicted value and there is a ground truth value and what is the confidence score. So here 96% it says sandal and 4% it says some other class. So like this we can plot multiple plots and visualize. So I am going to take 5 rows and 3 columns. So altogether I am going to take 15 images. So 5 into 3, 15 images I am going to plot and visualize. I am going to plot both the image as well as the prediction array. So let us plot and visualize. So here you can see from 25 images, you see here. So there is a wrong prediction here. So the prediction says it is sandal, but the ground truth value is sneaker. And the algorithm says it is 99% confident it is that sandal. But it is a wrong prediction. Since it is a wrong prediction, it is indicated in a red color. The right prediction is represented as a blue color, but its probability score is very low. So that is how a TensorFlow model can be utilized to classify the images in a Fashion MNIST dataset. Okay. Thanks for watching. Please subscribe for more technical learning. So you can find the code in this GitHub repository link. Thank you.